A square oscillator. A square object of mass m is constructed of four identical uniform thin sticks, each of length L, attached together. This object is hung on a hook at its upper corner. If it's rotated slightly to the left and then released, at what frequency will it swing back and forth? So this is our object. Four identical thin uniform rods, length L, and we can see here that because this is a symmetrical object, the center of mass will be right in the middle. And if you consider the center of the third and fourth segments, we can see that they're at a distance d3 and d4 from the pivot point, which are equal distance, and the center point is at a distance L over 2 from the end point. Okay, so this is actually a physical pendulum, so let's remember what we know about physical pendulums. We have a physical pendulum that is made of four identical uniform sticks, and let's recall what we know for a physical pendulum. So a physical pendulum we can think of as an arbitrarily shaped object. So for example, an arbitrarily shaped object like this. And if this is our pivot point here and the center of mass is located at a distance d from the pivot point, this is at a distance d from the pivot point, and it has been rotated through an angle theta, we will have the weight of this object, if it has mass capital M, the weight of this object will be appearing at the center of mass as mg. So this is our center of mass, and there will be a torque effect due to the weight of the object about an axis that goes through the pivot point. And if we write the net torque acting on this, it is, if we consider the perpendicular component of the force, so this angle is also theta, this will be the perpendicular component of the force, that is mg sine theta. If the angle is increasing in this direction, the torque will be minus mg d sine theta, which is equal to moment of inertia times the angular acceleration alpha or theta double dot. And for small angles, sine theta can be replaced with theta for small angles, and we basically obtain the equation of motion for the simple harmonic motion. So we can see that theta double dot, the angular acceleration, is equal to minus mg d over the moment of inertia I times angle theta, which tells us that the angular frequency omega will be a square root of mgd over I. That's the square root, and that's 2 pi times the frequency of small angle oscillations. Therefore, the frequency will be 1 over 2 pi square root mgd divided by the moment of inertia I. Okay, so now we're going to concentrate on this pendulum. So now for this pendulum, we need to know what the moment of inertia is and what the rod is, what the distance from the pivot to the center of mass is. So since the rods are uniform, and they're identical, the center of mass of this system of four rods or four sticks will be at the center of the object by symmetry. So we can see that the center of mass will be located right in the middle here, equidistant from the four corners. Okay, and what is the distance to one corner here? You can see that it will be the distance d. So the distance d will be equal to half of one diagonal length, L square root 2 over 2, or L divided by square root 2. So you can see we have a 90-degree angle here, and we have the same distance from the two sides, and these angles are 45 degrees. So when we have the distance from the center to the pivot point here, it's going to be equal to a half a diagonal length, which will be L square root 2 over 2. So that's what we would normally see. Of course, this is assuming that we have a small angle theta here. So this would be identical to this situation here when you consider the center here. This is L square root 2 over 2. That's the distance. Now, we need to recall the moment of inertia of a uniform rod. So let's do that. Now, recall the moment of inertia for a uniform rod or a uniform stick, and that's for a rotation axis that goes through the center of mass. So this is for center of mass axis rotations. So if we put the uniform rod on the x-axis here, starting from x equals 0, extending to x equals L, if we pick a mass element dm with the mass density lambda, which is the total mass divided by the length times dx, this will be equal to dm. So the moment of inertia for the center of mass axis rotations will be the integral r squared dm. So it will be the integral from 0 to L. So this mass element, is at a distance x minus L over 2 from the center of mass location. So it will be x minus L over 2 square r squared dm. dm is lambda dx. Lambda is our uniform mass density, which is total mass divided by length. So this will be lambda times the integral from 0 to L, x squared minus xl plus L squared divided by 4 dx. And if we perform this integral, this is going to be lambda L cube divided by 3. It will be x cubed over 3 evaluated between 0 and L. And then we will have x squared over 2, which will give us L squared over 2. So this will be minus lambda L cube over 2. And then we have this term, which is L squared over 4. So that gives us x, which is L. So this is going to be plus lambda L cubed over 4. And if we put this in the common denominator, we have 4 plus 3 minus 6 divided by 12. And for lambda, we substitute mass divided by the length for uniform mass distribution times L cubed, which gives us mL squared divided by 12 for the moment of inertia. Now, if we use the parallel axis theorem tells us that if we have a rotation axis that is parallel to the center of mass rotation axis, for the segments 1 and 2 here, so these two segments 1 and segment 2, we have, because the total mass is m, and 4 identical rods, each will have a mass m over 4. This will be m over 4 L squared over 12 for center of mass axis rotations plus m over 4 times the distance between the center of mass axis and the new axis squared, which is L over 2 parentheses squared. That will be L squared over 4. So this is our parallel axis theorem. So this gives us m over 4 divided by, we have 3 over 12 L squared from here and plus 1 over 12 L squared. So that will give us 4 over 12, which is 1 over 3 L squared over 3. So this gives us mL squared divided by 12 for segments 1 and 2. For segments 3 and 4, if you consider the distance from the center of mass of this rod to the pivot point, so our new rotation axis that is basically parallel to this axis, this distance is L, this distance is L over 2, so D3 is the hypotenuse of this right triangle, so D3 square is L square over 4 plus L squared, which is 5L squared over 4. So we see that D3 is square root 5 over 2L. So that is the distance between the rotation axes. So from this, I can calculate the moment of inertia for the third and fourth segments to be the I center of mass, which is m divided by 4 L squared over 12, and then plus md squared, where d is the distance between the two parallel rotation axes. It will be m over 4 divided by 5L squared over 4, that's D3 squared. D3 and D4 are the same here, between the distance between the rotation axes, D3 and D4 will be the same. So this will give me m over 4 times, we can see that this is going to be multiplied by 3, so that will be 15 over 12, and then I have 1 over 12 here, which will be 16L squared divided by 12, and this will be equal to, this 4 will make this one 4 over 12, which is 1 over 3, mL squared divided by 3. So if I calculate the total moment of inertia of this object, I have two rods, segments 1 and 2. They each have moment of inertia mL squared over 12. Segments 3 and 4 each have moment of inertia ml squared over 3. So it's 2 ml squared over 3. So I will see that I have 4 times 2, 8 over 12, and then I have 1 over 12 here. So it's going to be 2 ml squared over 12 plus 8 ml squared over 12, 10 ml squared divided by 12, which is 5 over 6 ml squared. Then I can substitute the result I have obtained. The frequency of oscillation is 1 over 2 pi square root of mgd over I. So m is the total mass m, g for the distance between the center of mass and rotation axis, we have L over square root 2, mgl over square root 2. And then we have mgd divided by I is 5 over 6, I total is 5 over 6 ml squared. You can see that the m's will cancel, one of the l's will cancel, and this will be in square root inside the square root. And this will give me my final answer for the frequency of small angle oscillations to be 1 over 2 pi 6g divided by 5 square root 2 L square root. So this is the final answer. Okay, so let's take a look at what we did here. We have a physical pendulum that consists of 4 identical uniform rods. First, I started by reviewing the physical pendulum. If I know the distance between the pivot point P and the center of mass, this distance is d, the weight is going to apply a torque on this object in order to restore the original vertical position so that the vertical axis will go through the center of mass, and this will be r cross f, so that's going to be d multiplied with mg sine theta, but in a direction that is decreasing the angle theta, so it's negative. Minus mgd sine theta is I alpha, and for small angle sine theta is theta, so we have theta double dot is minus mgd over I theta, which is in the form x double dot is equal to minus omega square x. That is simple harmonic motion. So I can recognize omega to be square root mgd over I. That's 2 pi times the frequency. So frequency of the small angle oscillation is 1 over 2 pi square root mgd over I. Now if we apply this result to our physical pendulum here, the total mass capital M here is the total mass of the 4 rods, that's m. And then we have d, the distance between the center of mass and the rotation axis. The center of mass is right in the middle, and the distance between the center of mass and the rotation axis will be approximately equal to here L square root 2 over 2, if this is a small angle. So that will be our distance. And for the moment of inertia of this full object, we can consider the moment of inertia of a uniform rod for center of mass axis rotations, ml squared over 12, and then we can use the parallel axis theorem. For the first one and the second one, these two segments, the distance between the pivot point and the center of mass is L over 2, so we add to ml the mass m over 4 for each segment, L squared over 12, the m over 4, L squared over 4, the distance squared between the two rotation axes. And as for the distance between the center of mass of segment 3 and 4 and the new rotation axis D3 and D4, they should be equal, and they're given by the hypotenuse of this right triangle. So that distance is square root 5L over 2. So that gives us a moment of inertia using parallel axis theorem again of ml squared over 3 for each stick. So for two sticks we have 2 ml squared over 3. For segments 1 and 2 we have 2 ml squared over 12. So the total is 5 over 6 ml squared. So if we substitute that here and we substitute for d L square root 2 over 2 or L over square root 2, we reach our final frequency 1 over 2 pi square root 6g over 5 square root 2 L.